Well, you might guess, if you've been doing a lot of thinking.
I've been doing a lot of thinking.
That's good. You might guess that a higher order derivative is much like in Calculus 1. Second derivative is the derivative of the first derivative. The third derivative is the derivative of the second derivative, etc. So things are going to behave just like you expect. So here's an example. Given a vector valued function, this helix r of t equals cosine ti plus sine of tj plus 2tk. We want to find the first derivative, the second derivative, which is the derivative of the first derivative, the dot product of the first and second derivative, and the cross product of the first and second derivative. Remember, the dot product will give us a not a vector but a scalar, actually a regular function in this case, and the cross product will give us another vector. So r prime of t, well, the derivative of cosine of t is negative sine of t, so it's negative sine of ti, and the derivative of sine of t is cosine of t, so it's plus cosine of tj, and the derivative of 2t is 2, so we got 2k. Easy. The second derivative will be the derivative of the first derivative, and so the derivative of negative sine t is negative cosine t, so we got negative cosine ti. Derivative of cosine t is negative sine t, so we got minus sine of tj. Derivative of 2 is a constant, so we could say plus 0k, but usually I don't bother to write that. So interesting that the first derivative is a circle in the plane where z equals 2, because the k component is constant. And the second derivative is a circle in the xy plane because the z component equals 0. So let's look at the dot product. Dot product r prime dot r double prime would be this vector dotted with this vector. So multiplying the I components, we got negative sine t times negative cosine t, and that would give us sine of t times cosine t. And multiplying the j components, we get cosine of t times negative sine of t, and that would give us negative cosine t sine t. And we multiply the k components, we got 2 times 0, so that's 0. So if you add all this up, turns out the dot product of those two vectors is 0. The cross product is a little bit more complicated, but the mnemonic device for finding the cross product, remember to set up the 3 by 3 matrix with I, j, and k across the top row. If we expand about the top row, we have I times 0 plus 2 sine t, so there's that part, minus j times its minor, strike out this row and this column, so we have negative sine t times 0, so 0 plus 2 cosine t, so we should have well, 0 plus 2 cosine t, but remember it's negative j, so we wind up with negative 2 cosine tj. And for the k component, let's see, you have k times sine squared t plus cosine squared t, and it's positive k. Remember this sine thing goes, the secant thing goes plus, minus, plus, so this is plus sine squared t plus cosine squared t. Well, golly, if that doesn't amount to 1, then I'm not sure what does. It turns out that my software didn't simplify that, which is a surprise, but my mind can do that, and my mind says this is 2 sine of t plus minus 2 cosine I, sorry, I'll try again. The cross product is 2 sine of t I minus 2 cosine of t j plus 1 times k, the 1 coming from this sine squared tk plus this cosine squared t k.